I el que farem serà passar directament a la següent xerrada, a més així recuperem una mica el decalatge que arrosseguem des del principi, que serà sobre astroquímica del doctor Stefan Brumley, que és investigador de l'Institut de Química Teòrica i que està aquí amb nosaltres. Doncs moltes gràcies i endavant.
So, good morning, everyone. Like just said, my name is Stefan Bromley, and I run the Nanoclusters and Nanostructured Materials group in the Institute of Theoretical and Computational Chemistry. In the next 15 minutes, I want to tell you a little bit about the dust between the stars, about its importance, what it is, and finally, a little bit about how computational chemistry can help understand this material. Thus, I've named my talk Simulating Stardust. So, most of you probably are not very familiar with dust, or at least you don't think you are. But when you look up into the night sky and you see the Milky Way, the Via Láctea, you see stars, many of them. Oops, sorry. Well, you don't see any stars now, so. Sorry, a bit of technical help. Okay. Okay, so we see the stars. So you look up, you see the stars, but you also see dark patches. So the dark patches are the dust. This is what's blocking the light from stars behind. So everybody's seen dust. It's the stuff that blocks the stars. And for many years, astronomers thought this was a hindrance. They didn't like this dust because it was blocking the starlight, and the stars were the interesting thing. But in the last few decades, the dust itself has become a primary object of study. It's become very, very important. It enables chemical reactions to take place. It has a lot of interesting properties, and it's ubiquitous. It's everywhere. So dust is not just in our Milky Way, in our galaxy. It's in every galaxy. Here, for example, is another galaxy. This is the Andromeda galaxy, a fairly close one. And we see the same pattern. We see bright regions, and we see dark regions. And again, the dark regions are the dust. But we can't see it, it's dark. But you can see it if you look in the right wavelength. So if you look in the infrared, if you look at the traces of a bit of heat that's left over from the dust, then you see this. So this is an infrared picture of that same galaxy, and then you see the dust. There it is, and it's easier to see if we combine those two pictures together. You see that they're complementary. You see the dust is exactly where the dark patches are. So there's how we see. So that's the first thing. First thing to remember, how do we see dust? We use infrared light. So where does dust come from? Another question. Well, it comes from stars. Here's what we've got to consider is how stars form and how stars evolve. So I'll take you through a little bit of this. I'm not an astronomer, but I think I can give a little bit of an explanation for you. There's two cycles here, one over here and one over here. We'll ignore this one for now. It's still very important, but it's for very, very large stars, where we have the supernovae and black holes. All the exotic phenomena still produces a lot of dust, but the primary way in which dust is formed is on this cycle here. So let's start somewhere familiar, the sun, a sun-like star sitting at the top there. Well, what happens? Well, we have to wait a few billion years, and then it becomes a red giant. So what's happening there? So what's happening when the sun becomes a red giant in a few billion years? It's starting to run out of fuel. A fuel for a star is hydrogen. Hydrogen fuses together to make helium. This gives off heat, the radiation that we see and need. But when that fuel runs out, it starts to then fuse other materials. And then exactly as we see here, it starts to cool down and starts to expand. And this is exactly the time in which dust is formed. So dust is being formed in the outer layers of the star as it cools down, as it starts to fuse new material. So helium, and we'll see in a second what else it produces. After that, this dust is then expelled into the interstellar medium. It's pushed out actually by the radiation of the star. And it forms a so-called planetary nebula. It's nothing to do with planets. It just looks like a planet. When people first saw these things, and you can see them, you can observe them, they look a bit like planets. So it's just a visual thing, but nothing to do with actual planet formation. So this dust is then expelled out into the interstellar medium. But eventually, again, wait a few million years, and then it will start to condense. It will start to aggregate and start to form nebulae, such as this one here. And this is now the birthplace of new stars. So the dust has gone full circle. It's been formed in a dying star, it's been pushed out into space, and then formed as a birthplace of new stars. And those new stars and planets are made from this dust and gas here, and then we start the cycle again. The new generation of stars, which will get old and produce dust and so on and so forth. So we need to understand what's happening around here, this dust formation. What's happening, I just told you, that the star, as it gets older, is running out of its hydrogen fuel. But then it starts to fuse, instead of hydrogen and hydrogen to make helium, it starts to fuse helium with helium and the other nuclear synthesis reactions. We don't need to go into the details, but other elements are formed at this latter stage. So let's have a look at what those elements are. Well, we've got hydrogen, of course, and helium. But after that, we start getting more heavier elements, such as carbon, oxygen, neon, magnesium, and silicon, and even up to iron. These are the more common elements formed. This is a schematic showing these like an onion-like picture. Actually, it's obviously much more complicated than this. There's lots of convection going on. But really, the important elements are these. So these elements, really the most important ones for us are carbon, oxygen, magnesium, and silicon. And of these four elements, two are particularly important. And those are carbon and oxygen. It's amazing, but the whole material that we are made of, this planet is made of, everything is made of, is determined by the ratio of carbon and oxygen in the outer regions of large stars. It's the balance between these two elements that gives rise to the type of dust that is formed, and thus all the things that we're made of. It's very simple chemistry. So what if we had an equal amount of carbon and oxygen? Well, then what would happen is you would make a lot of this thing, a carbon monoxide. Carbon monoxide is a very, very strong molecule. It can resist the very high temperatures around a star, and that's all you'll have. You'll just have a lot of carbon monoxide. We usually don't have simply an equal number of oxygen and carbon atoms. We tend to have an excess of one or the other. If we have an excess of carbon, as you might imagine, then we can form carbonaceous material, organic molecules and dust, and that is what we're made of. Life is made of carbon. Carbonaceous materials, carbon-based molecules. So this is absolutely required, of course. But more commonly, actually, we get an excess of oxygen. And then that oxygen reacts with the remaining elements of silicon and magnesium to make this stuff here. And this is called silicates. And this is the primary and most common solid in the whole universe. So most of the solids between the stars is made of silicates. So I'm not counting stars as gaseous or plasma type material, but solid material, silicates are the most common. So what is a silicate? A silicate is, like I just told you, is something that forms from the reaction of silicon and oxygen here and magnesium. It's normally formed, the basic unit is this. So a silicon atom sits in the center of an oxygen tetrahedra. Often geologists and mineralogists like to just put it as a tetrahedra. It simplifies the picture. And then we can think of these tetrahedra as bonding like this, for example, corner sharing. And this is the material known as silica, SiO2. But I told you silicates are a bit more complicated. They've got other atoms, so magnesium likes to intercalate between these tetrahedra, or even iron, and these are silicates. So silicates are a bit more complicated than pure silica, but they are basically based on these tetrahedra interspersed by magnesium ions. I told you silicates are everywhere, including the Earth. Have you ever thought why the geology of the Earth is based on the rocks that we see? It's all due to this stardust. Stardust is the precursor of planets. Our planet is made, the mantle and the crust are made almost totally of silicates. The reason for that? Because it was formed from silicate stardust. All rocky planets will have this similar type of morphology and geology purely because silicate dust is the most common solid matter in the universe. So that's important. So we've seen what it is, where it's formed. How big is it? How big is dust? Well, let's start again somewhere familiar. 1 meter. This dog is about a meter. Okay. What if we go 1,000 times bigger than the dog? A barrier of Barcelona, for example. 1,000 times more. Country, my home country, about 1,000 kilometers. 1,000 times more, we get to more or less a small star. So this is like a gigameter, so a million kilometers across. That's how big a star is. What about dust? Well, we're going to go smaller. Smaller than the dog. 1,000 times smaller than the dog, a millimeter. 1,000 times smaller than a millimeter, more or less a virus type size. 1,000 times smaller than a virus. That's the size of dust. It's of the order of 1 nanometer. So linking these two scales, a million, million, million. So nature has decided, in order to make dust, in order to make us, in order to make planets, it has to produce something a million, million, million times larger than the thing it makes. So what we need to understand, we want to understand processes around this star here, but we have to go down to this scale here to understand those things. So it's a crazy way in which the universe is made, but that's what we've got to accept. So how do we get this dust? It's tiny, tiny nanometer-sized dust. It's everywhere. It's between the stars. It's between us and the stars, between the Earth and the stars, interplanetary dust. We can go and grab it. So we can send up missions, and that was done actually in 1999, the Stardust mission of NASA. And they sent up a probe, and they actually captured some dust, and here is the collector here. And they indeed found silicates and other things as well. It was a very successful mission. But obviously that's not practical. We want to know the dust around another star. We can't send a probe to our next star. So what astronomers typically do is, is actually look at the spectra. And I've already told you what to look for. We have to look for the infrared signal. Okay, so I already told you at the start of the talk, the way we see dust is by looking at infrared light. And this is an infrared spectra. So we've got the wavelength of the light here and the intensity of the absorption here. And this is a typical spectra of silicate dust. And it's got two main features, one here and one here. And these are quite easily assigned chemically to this type of vibration of the atoms here, a silicon and oxygen atom, or this type of bending motion here. So we know the characteristic motions, and now we're getting closer to chemistry, you'll see. So we're moving from observational IR spectra down to the motions of atoms. And this is where we start to come in as computational chemists. Now, up until now, the detailed spectra that we have of dust has been quite poor. But just in October of this year, there'll be an extremely important mission launched, and this will be the James Webb Space Telescope. So just to give you an idea of the scale of this thing, this is the mirror in the James Webb Space Telescope that's going to be launched, and this is the Hubble primary mirror here. So it's order of magnitude, or twice as big as Hubble. And Hubble, as you know, you've probably seen beautiful Hubble pictures of nebula and various things. Hubble was mainly in the visible, whereas JWST will be primarily in the infrared. So it'll be an infrared telescope, and we are part of that, so that my group is a part of a project. We've got observing time on the new James Webb Space Telescope, and we'll be helping the astronomers to interpret their observations of interstellar dust. So how do we do that? Okay, we use computational resources. I told you we're modelers. We're very lucky. In Spain, it's got exceptional resources for supercomputers. We have a whole network all over Spain so the Red Española de Supercomputación, many, many resources, all of which we can use. But the main resource of this network is, of course, the Mare Nostrum Supercomputing Center in Barcelona, which is the most powerful of all of those nodes. So this is a great resource to have. And what do? Well, we do two things. We model the dust grains. Here's one here. We model them at the atomic level, and we look at the physical and chemical properties of those grains. So processes that happen on the grains, the structure, and so on. And of course, what is important for the astronomers, we look and interpret and simulate the IR spectra of these objects. So here is just an example. This is a cover we had in a recent paper outlining our contribution going from modeling to spectra to observation. So the last couple of slides, I'd like to just show a couple of movies. Hopefully they work. Yep. Okay. So this is the kind of stuff we do. They're very, very schematically, but okay. So on the left here, we have a silicate grain, a very, very small one, that's growing. So what we're sending in atoms of magnesium or oxygen or silicon dioxide or silicon monoxide, and this thing is growing, but as you'll see, it's moving. And it's important that it's moving because we want to get those vibrations, and those vibrations lead to the infrared spectra, which is what we simulate on the right here. So that's the way in which we come in. And we go all the way to this sort of size, typical sort of size. We get to 3,000 atoms or so. This is a dust particle of just 3 nanometers across. To give you an idea of how many atoms you need to get 3 nanometers across, it's about 3,000 atoms. You have to model all the individual motions, and the growth here. You see a silicon monoxide particle coming in here. And this is growing and moving. And we then, via these motions, we can then calculate the IR spectra, which then can be compared directly with IR observations from such as the James Webb Space Telescope. Okay, so hopefully that gives you a flavor where does come from and how theoretical and computational chemistry can help. And I'd just like to finish there with a summary. So silicates are the most abundant material in the universe. Thus, they're pretty important. It's found everywhere. Everything from circumstellar disks to interstellar space, comets, exoplanet atmospheres. The importance will be shown when the James Webb Space Telescope launches in October, and we will collaborate with those observations, and we will be essential for interpreting those observations. So, thank you very much for your attention.